Hello, physics students. Welcome to the lecture about simple machines. I am in West Valley City at the Maverick Center today, working with the FRC robotics team and their regional competition. If you happen to have free time on Friday, since you don't have school, the competition continues Friday and Saturday, and it's free and open to the public. And I would encourage you to come see some really interesting robots competing. That's at the Maverick Center in West Valley City. So in any case, to the business at hand, we are talking about simple machines today. So you should have a packet of lecture notes and you should have a packet of simple machines practice, and we'll be doing both of those things in two separate videos, I should say. So make sure your name's on your lecture notes. And before we begin talking about simple machines, we need to review the basics for energy. So we need to remember what is energy, what is work, what is power, what is mechanical energy. That's actually on there, potential and kinetic, my mistake. What is the work energy theorem? And what does conservation of energy mean? I'd like you to take a moment and look at your lecture notes from Energy, Chapter 8, and perhaps the foldable you did for the 12 energy vocabulary terms, and see what you can remember about work, power, mechanical energy, the work energy theorem, and conservation of energy. Now would be a good time to pause the video. So starting back again, what I hope you have found is that the basic definition of energy is the ability to do work, which we recognized as a circular definition because we didn't know what work was. We now understand that work is equal to force times distance, as long as the push causes the moving. We know that power is the rate at which work is done, work divided by time. So we're starting to really understand how they're all three connected together. Mechanical energy, as you can see, is the combination of potential energy and kinetic energy, whenever those two things occur, or one or the other. The work energy theorem states that work causes changes in energy, and that the amount of work you do is exactly equal to the change in energy of an object. And then finally, the great big idea of physics, conservation of energy, says that energy can never be created or destroyed. It may change forms, or be transferred. I'm not sure how to spell transferred. Well, I think there's maybe too many R's in that, but it doesn't matter. Conservation of energy means that, as far as we can tell, energy is never created or destroyed. It may, however, change forms. For example, a falling ball changes from potential energy to kinetic energy as it falls, or it may be transferred from one object to another, such as in the case when work is done. Okay, so this is all stuff we should be familiar with. This is the foundation, however, for understanding simple machines. So in this lecture, as I have in the past, I've tried to bold type the items that you should be filling in your lecture notes. So a machine, and particularly a simple machine, is defined as a device for multiplying forces, or, for changing the direction of forces. A simple machine or a complex machine cannot create energy. That would be a violation of the conservation of energy, of the law of conservation of energy. But it can transform energy from one form to another, or transfer energy from one location or one object to another. Machines cannot multiply work or energy. The principle of machines particularly simple machines, is conservation of energy, where the work we do input to the machine has to be equal to the work the machine does output of the machine. Since we know that work is equal to force times distance, we can write this as force times distance on the input side of the machine equals force times distance on the output side of the machine. This is the foundational principle for simple machines, and we'll keep coming back to this over and over again. I'll abbreviate it as work in equals work out in my own notes. So our first simple machine is a lever. And you've already defined lever in your vocabulary. You understand that a lever is a beam or a stick that rotates about a point of support, which we call the fulcrum. In this diagram, the fulcrum is a little triangle shape. The point of a lever is that it allows a small force over a large distance on one side and a large force over a short distance on the other side of the lever, or the teeter-totter. You can think of it as a teeter-totter. So in this pink equation at the bottom here, we have little force times big distance. That would be on the left-hand side of the lever. The lever moves a large distance. And on the right-hand side of the lever, we have a large force moving over a shorter distance. This is the idea of work in equals work out. We trade force for distance. Here's a numerical example. So we have a girl using a lever to lift a boulder. On her end of the lever, so this is the input side of the lever where she is pushing, she can push the lever down a distance of 1 meter. On the output side of the lever, she's lifting a rock or a boulder, and the rock can lift, when she pushes down 1 meter, the rock can lift 1/4 of a meter. She wants to lift a 500 Newton boulder. How much force should she apply? So we come back to our main principle for machines. Input work equals output work. That means the force on the input side times the distance on the input side, I'm going to abbreviate DIST for distance, is equal to the force on the output side times the distance on the output side. And so the main concern here is figuring out which is the input and which is the output. So the input side is always the side you are using, the side you're pushing or pulling with. So the input side is the force we want to know. How much force does she exert? And she does so over 1 meter. On the output side is the lifting. So we lift a 500 Newton boulder. The weight of 500 Newtons is the upward force the machine pushes with. And the distance is 1/4 of a meter. If you're not fans of the units, you can rewrite this without units. I apologize for the sort of autofocus bonanza that's happening. So we have force times 1, so force equals 500 times 1/4, 125. So she pushes with 125 newtons, and the lever travels a distance of, nope, that's not what I wanted. I was trying to stop the autofocus. Let's see. I don't know if that will do anything, but we'll find out. So she pushes with 125 newtons over a distance of 1 meter. And as a result, a 500 Newton rock moves up 1/4 of a meter. So there are 3 classes or types of levers. Type 1 is like we just saw. It's like a teeter-totter, where the fulcrum is in the middle, so the pivot point is in the middle. You push on one side and you lift something on the other side. Type 2 has the fulcrum on one side, you push on the opposite side, and the load you're lifting is in between. Type 3 has the fulcrum on one side and the load on the other side with you pushing in between. So type 1 has the fulcrum between the force and the load. Type 2 has the load between the fulcrum and the force. And type 3 has the fulcrum at one end, load at the other, and force in between. Type 3 we'll only concentrate on in terms of the skeletal system and how our bones and muscles interact. The next kind of simple machine we'll be concerned with is a pulley. So a pulley operates just like a type 1 lever. Remember that type 1 is the teeter-totter type of lever. So a pulley operates like a type 1 lever with equal length arms. If the arms are equal and we look at the equation for work in and work out, distance and distance are the same, say 1 and 1, that means that the force in and the force out have to be the same. So because a pulley operates like a type 1 lever with equal arms, it only changes the direction of the force. It does not change the amount of force. So the points of contact where the rope is touching the pulley act like the points where the input and output force are exerted. The pulley rotates about its axle in the middle, and the length of the radius from one side to the other is the same. So equal length arms, equal amount of force, input and output. But a fixed pulley, as we see here, only changes the direction of the force. Our other option for a pulley is a movable pulley. In that case, the pulley is not fixed to a permanent location. The pulley moves as the rope moves. Instead, the pulley's axle is connected to the load that it's lifting. A movable pulley acts like a type 2 lever. So we have the axle here, the rotation point, at the point of contact with the rope on the left side in this diagram. We have the input force, the point where the rope contacts the pulley on the opposite side of the pulley. So that's 1 diameter away. And our output force is where the load is lifted, so at the axle, at the center of the pulley. So this is a system, a pulley, a movable pulley acting like a type 2 lever increases the force by 2. So the input force gets to be half of the output force. And we'll talk more about mechanical advantage and how we figure that out in a moment. The third type of simple machine we'll look at is inclined planes. That's just the fancy word for a ramp. So a ramp increases or decreases the amount of force you need to exert to lift something. And we'll assume at first that the ramps are frictionless. The input force is the horizontal push you give up the plane, so this lady pushing on the ice block up the plane. The output force is the force it would take to lift the object by itself without the plane, so the weight of the object. The input distance is the length of the plane, and the output distance is the height of the plane. So, mechanical advantage is a way to talk about how much a simple machine increases or decreases force. So mechanical advantage is, and I'm going to abbreviate it in my own writing as MA, is output force divided by input force. The output force is usually the weight of the object, the amount of force required to lift the object straight up on its own. And the input force is always the amount of force you exert when using the machine. So we previously found that this girl using the lever we were shown before could exert 125 newtons of force and lift a 500 Newton boulder. So we can find the mechanical advantage of this lever by dividing the output force, which is the weight of the boulder, by the input force we found to be 125 newtons. I need my calculator to finish this. In fact, I'll need the calculator a few times. The glare may make it so that you can't see the screen. Let's see if I can, there. Okay. So we have 500 divided by 125, and that's equal to 4. So the mechanical advantage of this lever is 4. That means she can increase her 125 Newton force by a factor of 4, lifting a maximum of 500 newtons. Since input work equals output work, mechanical advantage can also be expressed in terms of distances. So sometimes we know about the forces and we say mechanical advantage is output force over input force. We can also say mechanical advantage is equal to input distance divided by output distance. That's convenient if instead of knowing the forces, I know the dimensions of the machine. So here we have the ramp we saw previously. We want to know what's the mechanical advantage of this plane. We can't talk about forces because we don't know how much this ice block or whatever it is weighs, and we don't know how much force she's exerting, but we do know that the length of the ramp is 5 meters and the height of the ramp is 1 meter. So the input distance is 5 and the output distance is 1. The mechanical advantage of this ramp is 5. she should get to push with 1/5 the force he needs to push with to lift the block straight up. You can find mechanical advantage of pulleys by considering the equal length type 1 lever versus the type 2 lever, where the load is halfway from the end of the lever. Or you can count the number of ropes supporting the object. So we talked about how a single fixed pulley has a mechanical advantage of 1, or has no change in force, which we now understand to mean a mechanical advantage of 1. We can also see that this box is supported by a single rope. So again, mechanical advantage equals number of ropes supporting the object, that's just 1. The single movable pulley, however, is supported by the pair of ropes. This rope loops under the pulley and the pulley supports the box. So both of these ropes are supporting the box. This is equivalent to standing on 2 bathroom scales evenly, and the bathroom scales each read half your weight. In this case, each rope segment supports half the weight of the box. So 2 supporting ropes means a mechanical advantage of 2. In the block and tackle system shown on the right, we have a combination of a single fixed, which does not change the force, and a single movable, which changes the force by a factor of 2. So again, we only have 2 supporting ropes here. The third rope just loops over the top to be held by this person. The mechanical advantage of this system is only 2. So, in an ideal pulley system, a woman lifts a 100 Newton crate by pulling downward with a force of 25 newtons. For every 1 meter she pulls, how much does the crate rise? In order to answer this question, we're going to consider the input and output work. So we're going to consider force times distance in equal to force times distance out. So on the input side, it's what she's doing, what she's pulling. She pulls with 25 newtons, and she pulls 1 meter of rope. On the output side, we lift a 100 Newton, so that's the weight of the crate, 100 Newton crate, and we want to know how far does it lift. So 25 equals 100 times distance. The distance, after dividing both sides by 100, is 1/4 of a meter, and 1/4 of a meter is the same as 25 centimeters. Our final sort of point of interest of a machine is efficiency. So we have the main idea that the input work equals output work. We have our next idea of mechanical advantage, a sort of rating of how well a machine can multiply force. Finally, we want to know how much of our energy is useful for a machine. So efficiency is defined as useful energy or work that's output by the machine divided by total energy that's input by the machine, multiplied by 100% to turn it into a percentage. Since mechanical advantage is related to the work done by the machine, we can also express efficiency as actual mechanical advantage. So that would be the ratio of the forces when the machine is in use, divided by theoretical mechanical advantage, which is the mechanical advantage we calculate using distances. Again, multiplied by 100% to make it a percentage. We'll see some examples of this in a little bit. So if we have a certain machine that's 30% efficient, what does that mean? What does a 30% efficiency mean? If a machine is 30% efficient, it means that only 30% of the energy you put in is useful work out, and 70% of the energy put in will be wasted. We use the term wasted sort of casually here. 70% of the energy that you put in will be converted into heat and other forms of energy that are not mechanical, that can't be used to do work. As a point of comparison, gasoline engines, so internal combustion engines, are at very best about 10% efficient. Think about that. Only 10% of the chemical potential energy that exists in the gasoline that you put into your engine is actually converted into useful work, into moving the car, running the air conditioner, playing the radio, etc. So finally, the last section of the textbook talks about energy for life. As you know, my expertise is physics and not anatomy or physiology. But in general, we say our bodies are machines, and so we have to have energy input. Our cells feed on hydrocarbons that release energy when they react with oxygen. And there is more energy stored in the food we consume than in the byproducts after metabolism. We don't need to talk about byproducts of metabolism, but the big idea is that we put energy into our body through the food we consume. Our body converts the chemical potential energy in the food into mechanical energy and some electrical energy. And there are byproducts of our bodies, and those byproducts have less energy than the energy held in the food before we ate it. So this ends our rather short lecture about simple machines. Your lecture notes should now be complete, and your lecture notes will go in your physics notebook, pages 43 to 47. Make sure they're in the right place. These will be part of the next binder check.